So what I thought I would do is I would start with one of my favorite riddles. So let's see, how do I want to do this? All right, so this will be centered. So you have an n by n board. So at this point, this is probably about 20 different problems start like this. All right? So the question becomes in these problems, how important is the number n? Does it really matter? And this is kind of like Conway's Game of Life, if you've seen something like that. If you are bordered by two, say, infected cells, you are infected and no chance of cure. So I am not up on my zombies. That's another professor in the department. Once you become a zombie, can you become human again? No. Is your question on what does it mean to be boarded?
Yes.
OK, that's what I'm about to get to.
Okay.
So diagonal does not count. Horizontal and vertical do. So if I have a configuration like this, if these two cells are infected, then this will become infected. If I have something like this, these two are infected, this one will become infected. All right. But if I have a situation like this, nothing is going to be infected. Okay? Everybody clear on the rules of the game? So if you want, we can call this zombie apocalypse. We've got enough zombies going on in the department. All right. Hopefully we'll have no zombies in the talk later today at colloquium, which should be an exciting talk, which will keep all of us awake, alert, and alive. But we'll see. Wait. We're not going to have any comments in class about this before the talk happens. So, what do you think would be a natural question to ask? If you haven't seen this problem before, what do you think would be a good question to ask? Yes?
Will the entire board become infected?
Will the entire board become infected? So obviously, what must be true before I start asking if the entire board is infected? I must know something.
Which ones start out?
Sure. So in a problem like this, they're never going to tell you which squares are infected. Why will they never tell you which squares are infected? It's too easy. You can just play the damn game. Right? Unless they make it extremely complicated. Imagine a 2014 million by 2014 million board where all squares with prime coordinates are infected. You know, they give you something complicated like this so bad that you can't do it by brute force. Otherwise, they'll give you some number of cells. So, question. If k cells are infected, must all cells eventually be infected? If anybody wants to be a smartass, please give me a value of k that will ensure everybody gets infected. N squared. Yes, if k equals n squared. All right. Anybody want to be a slightly less smartass? N squared minus 1. What else?
N squared minus 2.
So do you think we can do n squared minus 2? I see someone shaking their head. How?
2 by 2 board.
Oh, so if we have a 2 by 2 board.
Well, if you have a 1, then k equals n squared minus 1 doesn't work either. It's 1 by 1.
All right, so here we'll assume n is at least 2. All right, so if we have the 2 by 2 board, what's the problem? They could be next to each other. So if they start off like this, we have a problem. Okay? But as long as we avoid the 2 by 2 board, do you think we'll be okay if we just miss 2?
Not necessarily. Because you have a corner one, and then you just have 2 of them missing.
Ah, so one possibility is we have a corner board.
You can just place the 2 by 2 board in one of the corners.
Okay. So you want to miss which squares?
So like the top.
Miss these two? All right.
Yeah, yeah.
These two are,
No, it's just to the right. Move it over.
okay, these are not infected.
Yeah, that one and the one right below.
So then everything else is infected, right?
Yeah.
But, okay, but now these two will infect this one.
Okay.
And so the virus will spread. So first, this one gets infected, and then nothing else. Now that this is infected, this becomes infected, and then this becomes infected.
And that was n squared minus 4.
I'm sorry?
That was n squared minus 4.
Yeah, just move it off.
Oh, 2.
All right. So maybe if we have okay, so maybe if we have n squared minus 2, maybe everything gets infected. What about going in the opposite direction? No if what? 1. Can you do worse than that? 0. How high do you think you can drive it and still not have everyone infected?
Well, it depends if your board is.
And of course, any board.
Do n squared minus n because you could just like leave the entire top row.
All right, so one possibility is if we leave the entire row safe, then everybody else is infected. Shouldn't have drawn it so big. Yes? Wait, let's analyze this first. So if we have this case, will anybody in the top row get infected? All right, so we know that once we hit n squares that are not infected, there's at least one configuration. Yes?
You could extend that, so it'd be like n squared minus 2n minus 2n minus 2. Because you could just take out the whole perimeter.
So we could take out the whole perimeter. Okay, so no if, so now we're at k is equal to,
Minus 2n minus 2n minus 2.
2n minus, with the 2 inside there? Okay, so that's giving
Because
us,
you're taking the corners.
right. Another way of looking at it is we have n minus 1 things uniquely like this, and I have that 4 times. So I think it should be 4 times n minus 1. So 4n minus 4, yes. So now we're beginning to see that if we put things down very carefully, we can have large swaths where we will be safe. All right? So in looking at problems like this, one natural question to ask is, must all cells eventually be infected? And what is the critical value of n? Another thing is to say, maybe we are very selective in whom we infect. So the question is there a way to infect people in such a way that we will get everybody? So let's be more malicious now, more deliberative in our thought process. So now, what if you choose whom to infect? What is the minimum k you need? Yes? Excellent. So if you place them all along the diagonal, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So if we place everything along the main diagonal, then on the next turn, everything on the diagonal below and the diagonal above becomes infected. And now what do we do?
Same thing.
No, not same thing. That's not how you pronounce it.
Induction.
Induction, right? It's been it's been almost 15 minutes today without saying the word induction, right? If you look at it now, we now have a smaller board over here where the main diagonal is infected. And so by induction, that will propagate. So I will leave the base case of the 1 by 1 as an exercise to the reader. Okay? So if we strategically position n people, we can infect everyone. Okay? It's morbid? Well, it depends. If you want, you can look at it the other ways. We're developing a serum for zombies, and we can save everybody.
Yeah.
If you want to look at like...
Ebola in the news, it's too soon.
I'm sorry?
Yeah.
I'm sorry?
I said with Ebola in the news, it's
Oh, with the Ebola in the news, it's too soon. All right, so we will go to saving people. Okay. So can do with n.
What if the board is a torus?
Great problem. You can look at that later, but the solution for this problem has a really good math concept that I want to get on your radar screens. So we've just discovered that if we are deliberative, if we are careful, we can infect everybody if we infect the right n people. These are the trendsetters, okay? What's the natural question to ask? Can we do it with fewer? So in particular, can we do with n minus 1? So what I hope you see is that this is a reasonable question to ask. This is one of the possible flavors. So one flavor is you infect people randomly. Well, if you infect people randomly, you have the possibility of having a highly structured location of the infection where certain regions will be safe. And so I can carefully position it so I can have a huge number of people infected and keep the infection concentrated. So the other possibility, which is a little bit more interesting for this problem, turns out, what if I can choose for maximum carnage, for maximum damage, a certain number of people to infect? What is the most I can infect? So what do you think? Do you think we can do it with n minus 1? So how should we go about trying to prove this? Induction. Claim. N minus 1 is never enough. Case n equals 0. Laughable. I had one small chuckle, but...
I thought it said audible.
I can't write. There we go. At least we get a laugh now. So why is the case of n equals 1 laughable? There's no one infected, right? So if there's no infections, the infection clearly is not going to propagate, right? Let's try to do the case n equals, sorry, I should have written it in once. Case n equals 2. So that means we can only infect one square. Infection can't spread. Do you think these are good cases to build intuition? So, I mean, you are welcome to say either yes or no, but support that. This is math on the spot. I mean, these are the first building cases. I would argue these are not good cases to see what's going on.
I think we should start with like an n by 1 strip and show that if there's like you need to have something in there.
The problem with an n minus 1 strip is you have a different geometry. And here you can have people infecting you from above and the side. And so with an n minus 1 strip, it's not a bad idea to try to break this up into other cases and have the board length increase. But the difficulty is where you get to place things. Why do I think the n equals 1 and n equals 2 cases could be misleading?
Because you can't really see the structure of what's going on.
Why not?
It's not big enough. And you can't break it down.
You
Nope.
need at least 2.
You need at least 2 to have an infection spread, right? So when I'm looking at the case n equals 1 and n equals 2, is there any chance of the infection growing? No. So let's try case n equals 3. So 2 are infected. This becomes fun now. How many ways are there to choose the first square to be infected? 9. And God help us if we start doing it like this. because then there's 8 ways to choose the second. That means 72 cases to look at. It'll be really easy for me to fill up today's lecture, but it's not going to be fun. So how can we more efficiently go through the possibilities?
By symmetry, you can just look at the first 2 by 2 square as having all your possibilities. Because if like you stick it in a corner, then you can just rotate it to say, oh, and there's the other 4 corners, the other 3 corners.
Okay, so the first infection has to be in the square. We can actually do better than just in the square. In the top corner? Or so the 4 corners are actually identical. So you might as well assume it's in the first corner. Because when I look at the first square to be infected, I can always rotate. And if it's any of the corners, all the corners are the same. So that's one possibility. What else could I have? A side. What else could I have? So there's really only 3 possibilities. This is the same as trying to analyze tic-tac-toe. There are only 3 opening moves in tic-tac-toe under symmetry. So I'm going to be giving a math lecture or a math discussion in my daughter's kindergarten class. So I will probably be doing an analysis of tic-tac-toe. I know that they're going to have a better chance now on the playground against me, but oh well. So there's 3 possibilities. My first one infected is here. My first one infected is here. My first one infected is here. Now we start to look at where we could put the second. How many places do we have to put the second here? Up to symmetry. I don't care about doing things. How many ways can I do it? 5. I could put it here, 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 or here. So there's 5 possibilities. If I put it here, nothing else gets infected. If I put it here, this gets infected and then I'm done. If I put it here, these get infected, it fills in here, but nothing gets further. If I put it here, nothing gets infected. Here, nothing gets infected. So we can eliminate this entire case. Arguing similarly, you can eliminate this case, and you can eliminate this case. There will always be at least one square that's safe. Okay? So now the question becomes, how do we go further? Now, we could actually gather a little bit more information. So the question I'm just asking, is there at least one person who does not become a zombie? And the answer is yes. In all of these cases, there is at least one person who does not become a zombie. But that's not the best question to ask. What would be a better question to ask? How many? It might be useful to track in all of these and see how many people stay zombie-free. And in this case, how many people, worst case scenario, I think I have here and here. I infect those 4 here. These ones are all safe. I think worst case is 4 squares get infected. I don't think any more than 4 ever get infected. That could be useful information. So when you're tackling problems like this, I deliberately want to take some problems you have not looked at and discuss them live in the class. And try to go through the thought process. How would you attack something like this that you haven't seen? Look at small cases, try to build up intuition. And then the question is, what other things do you want to look at? One thing to look at is how many squares stay safe. That might give you a number to try to work on, that I always have this many safe. So it might be the case that you always have more than one safe, but that might be harder to prove. Okay. Anybody have any thoughts as to how we would try to prove this in general? Yes?
You do about an intuition that you can't infect a row that doesn't have something already infected.
That you can't infect the whole row or somebody in the row?
That you can't get a row, a row that doesn't have any infected cells, it cannot be infected.
Well, the problem with that is, so the question was, show that if you have a row that's not infected, it never gets infected. I could have something here and something here, and that will infect this element in the row. But what's the problem of having something here and here?
You don't have something. Oh,
Well, then row or column.
row or column.
So this will tell me that there's going to be a row and a column that does not have an element. Do I somehow get an infection there? Maybe a pigeonhole principle. an induction argument. So right now, I don't want to solve the problem. I want to talk about ways to try to solve it and things to try. So this was a great idea to say, hey, I have a row. The row is not infected. It's always not infected. So what you want to do is you want to create what's called an invariant. So if a row starts healthy, stays healthy. And then what you can do is you can look at what happens as the process evolves, as more and more cells get infected. And what you would love is if you had an invariant like this, then as time passes, if a row that starts off healthy stays healthy, you can never infect everything. If this invariant, if this was true, you would win. Unfortunately, this is false. But you have hit upon the right idea for the solution, or at least one of the right ideas for one of the solutions. Look for something that is unchanged as the virus propagates. So unfortunately, this is not the right thing to look at. And I'll give you a hint, it's not column. Yes?
If the bottom row stays healthy.
Right, but you might start off with something in the bottom row.
If the top n-1 square in this corner stays up, isn't
So the problem is these things are becoming inelegant. Right? This is a huge advantage of math problems, for competitions. The solution has to be elegant. As soon as you start using long language, you know you're on the wrong path. Or at best, you're on a needlessly complicated path. There's got to be a better way of doing this. I was taking a complex analysis class in college, and after doing 2 pages of computations, I wrote, there's got to be a better way of doing this. I don't know if I've told the story. And the professor wrote it, I did.
2 times.
Yes. Okay, only 2 times. That's not bad.
The last one was in grad school.
No, it was always, we can check. It was Peter Jones, so we can check the tape. And he wrote, it's about time you realize this. So for problems like this, there's typically a time limit. And if you start doing these long computations, you're not going to finish. Any other thoughts as to how we could try to approach this? What's the worst possible configuration? Even if we can't prove it, what do you think is really, really bad?
All one row at the bottom.
If you have all in one row on the bottom, that's great. The infection won't spread.
Have it on a diagonal.
Diagonal. So diagonals are the worst possible things. We're missing something. So in some sense, you want to say the worst possibility is if I have them in a diagonal, it's going to fill out. How do you make that rigorous? Another possibility is to try to do things by induction. And say, well, I know it. Let's imagine now I'm trying to build, I now have a 4x4. I look at these 3x3 corners. Maybe one of the 3x3s has to have at most a certain number of elements. Maybe things can't come in. It starts to get really complicated to figure out how to do this by induction. So what I want to do is I want to do something that's not quite as good as an invariant. The technical term for this is a mono-invariant. Quantity whose magnitude either stays the same or only increases or decreases as time passes. So for example, 1, 1, 2, 2, 1, 3, 4. Is this a mono-invariant sequence? No. What about 1, 1, 2, 2, 2, 3, 4? Yes. So I have a sequence, and it's either strictly going up, it's either going up or going down. You can stay locally constant for a time, but you can't go up and down. Okay? Can go up or down, not both. So how many of you have heard of these quantities before? Invariants, mono-invariants. These are some of the more obscure things in problem solving, but they're extremely useful. The difficulty is the same difficulty as the pigeonhole principle. What's the difficulty in pigeonhole? Finding the pigeons. What do you think the difficulty here is? Finding the quantity. So I remember years ago someone showing me the correct quantity to look at here. And it's beautiful. All right. So let's let Pn equal, ends by 10. Pt equals perimeter of infection at time t. So I look at each square that's infected, and I add the length of all the sides. Now, if two infected cells are next to each other, do I count the wall that they share? No. Okay, so you don't count common walls. Okay? So I claim PT is a mono-invariant. Do you think the perimeter is going to go up or go down? Why do you think it's going to go up?
Friends can get infected, but they can't get cured.
Okay, does this seem reasonable that it may stay the constant, but it's not going to go down as we get new cells infected? So let's look at what could happen. So imagine you have a configuration like this, and this cell was healthy, and you now infect it. Does your perimeter go up or stay constant?
No.
It stays constant. If you infect this cell, yay, it's infected now, you gain these two outside walls, but you lose these two inside walls. The perimeter has not gone up. So in this case, perimeter constant. Just 1 second, because this might answer your question. What if I had this configuration? What happens now? Was this your question? Yes. Perimeter decreases. It decreases? Let's see what happens. We fill up over here. We lose this, we lose this, we lose this. They're no longer perimeters. They're no longer on the outside. We gain this. We lost 3, we gained 1. Net effect? Perimeter decreases.
But don't you also gain the 2 left?
Yeah, but you lose the two. Like
Yeah, but it's after.
Over here? Down here?
Yeah.
I'm just talking about what's going on in this square here. We have to look at all the different ways for the virus to spread. And I'm saying
So
if,
it doesn't spread everywhere at once.
well,
It goes one by one.
I can break my analysis into each case. And so when I look at what's happening for each square, yes.
If the perimeter decreases, though, I guess that still would be fine, though, right? Because then when you fill in the other 2 squares as you go, then you would just be keeping the perimeter constant.
Well, we actually want the perimeter to be decreasing or staying the same. If the perimeter goes up, the infection is not only spreading, but it's increasing, in some sense, the region it's hitting. This is how we're going to win by the mono-invariant. We're going to show that initially the perimeter is too small to cover the entire region, so somebody has to be safe, and that somebody always has to be safe. So we have to look at all the different ways you can be infected. So I could infect by having things above. I could have not just things above, but above and on one side, above on the other side, 3 out of the 4. Okay, doesn't matter. If I have all 4 of them, the perimeter goes down 2. Decreases by 1. Perimeter decreases by 2. I need to look at now the infection case like this. What happens in this case? So now this gets infected. Same is the same. Perimeter constant. Do I have to worry about things happening on corners, or can I still view them in this general framework?
Didn't you decrease by 2 in that first
In the first one?
The second one.
Oh, you're right, decreased by 2, thank you. Yes. I don't have to worry about analyzing this corner separately. That's just a special case when I have just 2 things infected and just rotate. It doesn't matter that it's a corner. So here's the interesting fact. No matter who gets infected, the perimeter of the infected region cannot grow. So we have discovered a great mono-invariant. So the perimeter of the infected region is non-increasing. So this is a beautiful concept. We've associated to this problem this quantity, the perimeter of the infected region. So at the start, the perimeter of the infected region is what? What do we know about the perimeter of the infected region? It's at most 4 times the number of infected cells. It's less than or equal to 4 times the number of infected cells. So it's less than or equal to 4 times n minus 1, or 4n minus 4. Right? The best case to make the perimeter as large as possible is if no cell shares a side with another cell. Okay. What is the original perimeter of the whole set? 4n. Note, perimeter of the n by n square. So what does that mean if the perimeter of the whole n by n square is 4n and the perimeter of the infected region is 4n minus 4? Yes?
Never infect the whole region.
Why not?
Okay, sorry.
So why can't it infect the whole region? What's the contradiction?
The perimeter is always going to be decreasing, so your perimeter will never reach 4n.
The perimeter will never reach 4n. The perimeter is always less than 4n, so we can't have the whole thing infected, because if everything was infected, the perimeter would be 4n. Therefore, perimeter of infection is always strictly less than 4n. Therefore, always at least 1 square that's healthy. Okay. Yes?
When did we prove the mono-invariants?
Well, that's what we proved over here by breaking it up into all these different cases.
Okay.
So if I'm going to be infected, I could have 2 vertical or 2 horizontal, they're the same. I could have 3 out of 4. I could have 4 out of 4. Or I could have 2 in a pattern like that.
Okay.
Those are the only possibilities. And so we've shown no matter how a cell gets infected, it is not going to be able to increase the perimeter. So if you've never seen this before, this is an absolutely wonderful thing. How many of you have taken any physics classes? A good advanced physics class will talk about invariance. You might get Emily Noether's theorems about trying to understand physical systems by invariance of motion. So if you have something that's conserved, that's a big word they use in physics. So again, this is supposed to be a springboard class. I'm supposed to try to connect this to things that matter. Do you think this matters?
Yes.
Yes? Wow. Easy audience. To me, I'm not so interested about this particular problem. Now, maybe with Ebola and stuff like that spreading, if I didn't teach in this nice secure room all the way down in the sub-basement, I might be more worried about stuff like that. But the idea of a conserved quantity, this is central in physics. And so some of the biggest theorems in physics talk about you have certain conservation laws, and from those laws you can deduce things about the motion. This is very similar to what we're having here with these mono-invariants, with these invariants. Now, this should leave you a little bit unsatisfied at the end. Why should you be a little bit unsatisfied about this? Do you like the answer we get? Yes?
Because the number of
I'm sorry?
Oh, the number of squares that like have to be left healthy. Well, like, we didn't get that.
Well, all we get is that there is at least one square that's healthy. Let's try to imagine a board with at least one square that's healthy. Okay. Where should I choose my one cell to be healthy and everybody else to be infected? So, one cell healthy, the rest are infected. Like that, all right? Where do you want to put the one healthy person?
You can't,
You can't.
but you could if it was a 1 by 1 board.
Well, then that, but your primer will also be higher, so you have to go to 2 to get 50.
Yes.
There's at least one healthy person, but there's gotta be more.
There's got to be more. So notice that this immediately improves itself.
And we, in particular, we show that there have to be at least 4 healthy
Yeah.
people.
Why
Oh.
can't it be 2?
That matter.
There's one.
Why do we have to show there's at least 4?
No, we do explicitly show that, right? Because the number of infected people can ever get more than 4n minus 4 by that method.
So you have
So we can put a 2 by 2 square in one of the corners, and that's okay.
Oh, because you use.
perimeter
Yeah.
of 4n.
Okay, what I'm saying is, when we did this argument over here, we initially only got one square was healthy, right? Now what we're going to do is we're going to see what can we milk from that. We know one square is healthy. Do we have to have more than one square? So if the square is in the interior, if the square is even at a corner, we're still in trouble with stuff like that. So the question becomes, what is the minimum this guarantees? Yes?
Does it end?
I don't know. Haven't thought about it. That's a wonderful thing about teaching this course. Right? So I'm going to leave that as a question to you. What is the minimum number of squares, or better yet, let me rephrase that. What is the maximum minimum number of squares that you should be able to get from this method? We know there's at least one square that's healthy. I've heard arguments that there's at least 4 squares that are healthy. Maybe there's at least n squares that are healthy. And so that's the question is, can you improve this? Can you somehow feed this in and say, now that I know somebody is healthy, they can't have 2 infected neighbors? Right? So if I'm healthy, I have to have, I have some neighbors, at least one of my neighbors has to be healthy, and that neighbor has to have healthy neighbors. So everybody's eating right now, nobody's becoming zombies. So see how far you can push this. Can you push this to getting n people? I have deliberately not thought about it. No, don't think about it. No, don't think about it yet. So at home, waiting in line, listening to a colloquium, think about problems like this and see about how many cells must be safe, okay? And I will take solutions after colloquium for no, I won't say. All right. So I want to use the last 5 minutes to do one of the inequalities from the homework. Either the a to the a, b to the b, c to the c, or the a plus 1 over a squared. Does anybody have any preference? Second one? Okay. So this was the exercise a plus b plus c equals 1, a plus 1 over a squared plus b plus 1 over b squared plus c plus 1 over c squared. And the claim is show it is at least 100 over 3. All right, so I want to talk just in generalities about this. I've posted solutions. I want to hear a little bit about what people in class have done. When you have problems like this, you should always ask, what do you think the extreme case is? So as I vary a, b, and c, do you think I'm going to eventually get this to be really large or really small? Really large. As soon as an a, b, or c starts to get really small, the 1 over a, 1 over b, 1 over c is going to kick in. So probably your intuition is there's going to be a minimum. As I vary a, b, and c, there's going to be a minimum value. By symmetry, the minimum value is probably going to be when they're all equal. If I try a equals b equals c equals 1/3, that gives 100 over 3. And at some point, I should be using a plus b plus c equals 1. In a problem like this, can I always assume that a plus b plus c sums to something? Or do you think the value of this quantity is going to depend on what a plus b plus c sums to? So if I were to multiply a, b, and c by 2, do you think that will change the minimum value? What do you think? So if I replace a with 2, that makes this larger, but that makes this smaller. Right? So there is a huge disparity here.
Wait, are we changing a plus b plus c plus 1?
Yeah, what if we made it equal to 2? Do you think that's going to change things?
Oh.
What do you think the minimum value would be? Well, then if we made them all that, we'd have 2/3, and now things become a little bit low. So then the question is, what would we get if we took 2/3? So if we try, or let's do something better than that. Let's have a plus b plus c equals, what's a really good number to choose? 3, right? So if a equals b equals c equals 1, that's going to give us 2, 4, 8, 12, which is also known as 36/3. So if a plus b plus c equals 1, I'm sorry, if a plus b plus c equals 3, each one of them equals 1. If that's really where the minimum is, the value is now going to change. So when you have problems like this, you want to get a sense of when do things matter. Does it really matter that I have a plus b plus c equals 1? Can I renormalize? In the other problem on the homework, you could have actually renormalized and chosen b to be 1 if you want, because you had this nice scale change. If I change a, b, and c by a factor of r, I change both sides by r to the 2, a plus b plus c. Doesn't change anything. Over here, if I rescale a, b, and c by the same amount, all of a sudden, I no longer expect 100/3. So lots of ways to proceed. When you see something like this, think Lagrange multipliers if you've seen something like that before. The problem is when you try to do Lagrange multipliers, the constraint is going to be very easy. It'll give you 1, 1, 1 for the gradient of g, but the gradient of f is going to be complicated. What could I do to try to simplify my life here? So I have a plus 1 over a squared, b plus 1 over b squared, c plus 1 over c squared. What could I do to make my life simpler? I could square things. And if I square things, it's really nice because I have the a hitting the 1 over a. So I would get a squared plus 1 over a squared plus b squared plus 1 over b squared plus c squared plus 1 over c squared plus 6. And so I tried to use arithmetic mean, geometric mean inequalities with this. And the number of terms I had could either be 7 or as high as 12. I could make the 6 1, 1, 1, 1, 1, 1, 1. And the nice thing about doing something like that is the product of this is going to be, if I make the 6 as 1 plus 1 plus 1 plus 1 plus 1, I'm going to just get, the product will be 1. Unfortunately, it's not going to give as good of a bound as 100/3. So we've got about 2 minutes left. Does anybody have any good ideas how to approach this? I used another inequality, the Cauchy-Schwarz inequality. I'm wondering, did anybody solve this without using Cauchy-Schwarz? Okay, how did you do this without Cauchy-Schwarz?
Lagrange multipliers.
Okay, so you actually just went through the algebra?
It's not hideous.
So if you do Lagrange multipliers, you've got the gradient of f. Let's say f of a, b, c is a squared plus 1 over a squared, yada, yada, yada. The gradient of f would be 2a minus 2a to the minus 3, dot, dot, dot. The gradient of g will be 1, 1, 1. So we now say grad f equals lambda grad g. And so now what we get is 2a minus, I can drop the 2. I think a minus a to the minus 3 is b minus b to the minus 3 equals c minus c to the minus 3.
Yeah, those are one-to-one functions. So.
All right, so now you show that these are one-to-one functions. They're not one-to-one functions. You've got to be very careful. You can fix it. We don't care about these functions everywhere. Where do we care about these functions? is 0 to infinity. So for instance, if I place a as 2 and negative 2, oh, sorry. Is that what I want? I don't know, maybe I'm okay even with negative values. You got to be just careful about here. So what you're saying is that if I want to solve x minus x cubed equals some fixed number alpha, you're saying there's only one solution to this?
At least in the relevant interval.
Where they're all positive? Okay, so that's one approach, is to try to do a little bit of work to show that there's one and only one solution to x minus x cubed. This will give you a very special cubic. And cubics have either one root or 3 real roots. So this is definitely one approach. Anybody have another approach? So I had started that and then I abandoned that because I did not really like analyzing the cubic. But I will try to include that in the write-up if somebody can send me tech code on that. In the solution, I've talked about the Cauchy-Schwarz inequality. So what I will do is I will send you some stuff to read about invariance for Wednesday. If there are other topics you want to do, let me know. I thought invariance would be a fun topic. This is why I chose the virus problem.